Thank you very much. Short presentation. I'm Miglena Asenova, as just Rota introduced me, and I have a master's degree in pure and applied mathematics at the University of Modena and Reggio Emilia. I have also a master in mathematics education at the University of Bologna, and in 2017 I decided to start my doctorate in mathematics and computational science at the University of Catania, where I discussed the thesis in mathematics education. My advisors were Professor Bruno D'Amore from the University of Bologna, formerly, and now from the University Francesco José de Caldas, Bogotá in Colombia, and Professor Cinzia Cerroni from the University of Palermo. I thank a lot to my advisors. Currently, I am a researcher in mathematics education at the Free University of Bolzano in Italy since September 2021. The thesis I discussed in February 2021 is titled Categorical Definition of Mathematical Objects Specific to Mathematics Education. So it is a quite unusual topic and quite unusual thesis in our discipline, and this for at least two reasons. First of all, because I use mathematical tools in order to define something, to give a definition in mathematics education. And this is quite unusual. And also because it is purely theoretical thesis. That means there is no practical or experimental part in my thesis. Okay, the thesis was published in 2021. And I thank a lot to publishers this ebook, and I thank a lot to Professor Ferdinando Azzarello for reading the nearly 600 pages of the thesis and appreciating it, and for writing the preface, and also because we are working on some follow-ups of the thesis together with new PhD Sara Bagossi on some aspects related to my PhD thesis and to the PhD thesis of Sara. Okay, the outline, what I will speak about, first of all, the motivation to the research, then the research questions, then I will present the global scheme of the thesis and the answers to the research questions. Oops, okay, and this is, I think, all we can then also discuss a little bit about what I presented, and there will be also some interactive moments where you will be asked to answer some questions, some poll questions. Dorota will support me in doing this, and I thank a lot for this support during the presentation. Okay, let's switch to the motivation to the research. I think that many of you will wonder why one should define a mathematical object in mathematics education, because I think many of you will say, okay, are there not already definitions of mathematical objects? Why do we need such a definition? And so I examined 7 of them. We can see them shortly here. The first one given by Chevallard, where an object is emergent from a system of Praxema. Another given by D'Amore, where the mathematical objects are symbols of cultural unities that emerge from a system of uses that characterizes human pragmatics, and they continuously change over time, also according to needs. Then Redford's definition within the theory of objectification, where mathematical objects are fixed patterns of reflexive human activity incrusted in the ever-changing world of social practice mediated by artifacts. Then Duval's definition, where we have the mathematical object as an invariant of a possible multiplicity of semiotic representations. And then the definition within the other approach, the ontosemiotic approach, here formulated by Font, Godino, and Gallardo, where a mathematical object is an entity which is involved in some way in mathematical practice or activity, and which can be separated or individualized. Then here we have a characterization of mathematical object given by Svart and colleagues within the cognition approach, where They speak about discourses and routines, practical and discursive routines. And they state that the signifier itself, signifier in the sense of a symbol, together with all its possible mathematical object realizations, could be viewed as a new mathematical object. That means here they describe how a mathematical object is created. And last but not least, Dubinsky and MacDonald's definition or description of a mathematical object within the APOS theory approach, where an object is constructed from a process when the individual becomes aware of the process as a totality and realizes the transformations can act on it. You can see great semantical richness of definitions in our discipline. That means at least two things. From one point of view, we can say that there is no approach or theory in mathematics education that can abstract from the use of such a definition. So we can see that all the different approaches need to tell something about what a mathematical object is. But we have a lot of different definitions because we have different approaches to learning theories and so on. And this can be richness, the semantic richness, because it means that we are able to use different approaches to mathematical objects and to differentiate our research. But semantic richness can also be somehow confusing. And so I think that it would be important to construct, if possible, the general definition of mathematical objects that would act as a kind of boundary object that can be projected within the various theories and illuminate the different approaches to the mathematical objects without asking to tell which is better or worse, confronting them. Okay, this is one of the motivations to the research, but another motivation is the following one. Let's look to definitions like the following one, definition of function that we can find in textbooks and so on. This is a purely mathematical definition where we have relations between sets. We have the set theoretic language, which is the typical object language in mathematics. And here we have no of the aspects highlighted in the formal definitions. Where we have, in the formal definitions, we have the epistemic aspect, we have the semiotic aspect, we have the focus on processes and so on. Here, all those aspects are not present in this definition. So we should explain which are the relations between this kind of definitions and the other kind of definitions. It is natural that the definitions in mathematics are static and do not take into account the aspects I tell about formal, but and that in mathematics education we are interested in processes, but we should also consider that we cannot speak in mathematics education about concepts of objects because students have an object to have a concept of. And so what we can speak about are objects we are creating in mathematics education as a research discipline. So we create, but we are not creating objects in themselves. We create models that we use in order to interpret what we consider are the objects of the learning objects of students. And so we have first order models in this way, and we have also second order models, because when a mathematics education researcher takes the viewpoint of the epistemologist of mathematics education or philosopher of mathematics education, so he or she does not examine what happens directly in the classroom or in the mind of the student, but he elaborates or constructs second order models, interpretative models that explain how researchers in mathematics education do research on these topics. And so all those aspects should be a part of the definition we were looking for. Okay, this is the motivation to the research. Let's now come to the research question. questions. There are three research questions. The first one is this: which criteria should satisfy a definition of mathematical object specific to mathematics education? Then which theoretical fragments could allow to construct a theoretical framework that would be able to receive the criteria identified in the answer to research question 1? And then the last one, if it is possible to formulate a definition of mathematical objects specific to mathematics education in the theoretical framework identified in the answer to research question 1 that takes into account the criteria identified. Okay. You can see that the research questions are not independent from each other, but this is okay. So it's not so, because my PhD thesis can be conceived as a kind of constructive proof of existence of this definition. And so the answers to the research question 1 and 2 are necessary in order to be able to exhibit the definition that is the answer to research question 3. Okay. Let's come now to the global scheme of the thesis and the answers to the research questions. In order to present the global scheme of my thesis, I will use the SKT model drawn from Zalamea's work. Fernando Zalamea is a philosopher of mathematics who theorized the synthetic philosophy of contemporary mathematics. And in his works, he makes use of mathematical tools in order to analyze mathematical practice. So my PhD thesis is also inspired on his work, and I thank a lot to Professor Zalamea for the support in some of the most challenging moments of the thesis. Okay, let's start with imagine an oriented graph where we have 3 nodes. And we imagine each of that nodes as a kind of world where we have some rules, and we associate to each of that nodes or worlds part of the thesis. The thesis is divided in 3 parts, and each of the 3 parts is used to answer one of the research questions. So we have this part of the model, which is the key part of the model, SKT model. Who knows something about crypto models will recognize here some conceptual issues of this tool, but it's not necessary to know what crypto models are. What is important is to think of that the information present in the first world, on the first node, is included in the second, and what is present in the second is included in the third. And in this way, we also explain what I said former, that the PhD thesis is a kind of proof of existence. Then we associate to each of the nodes a structure, here represented by the dashed rectangles, and we insert in each of that rectangles the same structure. That means 2 spaces, we call them spaces, an upper space represented here by the green rectangle, and the lower space represented here by the green oval. And we imagine 2 functions, we call them here cognitive functions. Function that goes from the upper space to the lower space, and this is the synthesis function, and this is what is synthesized from the upper to the lower space. And we have the other function that goes from the lower to the upper space, and this is the analysis function. Synthesis and analysis are 2 cognitive functions that are very general, and we can use them in quite all disciplines, not only in mathematics education or in mathematics, but also in other disciplines. What we can imagine to be collocated into the upper space are processes, ideas, concepts, intuitions, and so on. And what is collocated in the lower space are the results. If we talk about mathematics, there can be, for instance, formalizable results, or simply in this case, the results of the first part of my thesis. The synthesis function from a mathematical point of view, it's a projection function, and the analysis function from a mathematical point of view will be simply the left inverse function of the projection function. How acts the analysis function? It acts creating meaning in our model here. The meaning is expressed by this red line we can see here, and it can be, the meaning function can be local or global. Local when the meaning is when the analysis function acts continuously, we can say, on all the lower space, and we have a global meaning when it acts only on subsets of the lower space, so we have only local meanings. Okay, in the result of my of the first part of the PhD thesis are the criteria the definition should satisfy, the definition we were looking for should satisfy, and the global meaning here is given by the invariances in theoretical approach to theory in mathematics education research, what we called top-down approach. This means we started from examining different approaches to theories in mathematics education research, and we extracted some criteria useful for our definition. And then also by the global meaning is given also by the invariances in empirical examples of mathematical objects specific to mathematics education, in approach to concepts and to definitions of mathematical objects in mathematics education research, as the 7 we saw former, and in mathematics, also approach to objects in mathematics. And we called this the bottom-up approach, because we started from examples and we abstracted, in this case, abstracted criteria useful for our definition, and by the progressive refinement of the criteria by analysis and synthesis. I didn't tell something about the methodology of research, but globally we can say that we adopted the pragmatist approach, where the research is led by the research questions. And locally we adopted various strategies. 2 of them are here, the top-down and the bottom-up approach, and also this SKT model. Okay, the second part of the thesis, here we have the same synthesis and analysis function. The result here was the theoretical framework, and the global meaning here was given by the coordination of the category theoretical model and its discursive counterpart in mathematics education by interpretation and modeling. What is meant by interpretation and modeling? Interpretation is mean that we take a fragment of category theory, and we associate to this fragment of category theory a fragment of theory in mathematics education research, and modeling is the vice versa. The third part of the thesis is we have the same structure. And here the result is given by the model of definition of mathematical object, and the global meaning here is the same as by the second part, this coordination of category theoretical model and discursive counterpart in mathematics education. And the tools are always the methodological tools, interpretation and modeling. So who knows somebody who knows something about algebraic topology will recognize here, I think, the basic idea of a sheaf. And this is the second part of the first part of the SKT model, the S part. So we can then also create connections between the first and the second part of the thesis. It is given by here by the criteria, by the fact that the criteria determined in the first part of the thesis are the presuppositions of the theoretical framework in the second part of the thesis. Then we can also create a connection between the second and the third part. Here the connection is given by the fact that the theoretical framework determined in the second part is the suitable context for the definition sought during the investigation. And finally, also a connection between the first and the third part of the thesis can be established, telling that the model of definition given in the third part satisfies the criteria determined in the first part. We speak of a model of definition and not of a definition because once constructed the definition, we began to be aware of the fact that it was really abstract, and we're an abstract definition, so it needs the interpretation in order to be used, and so we prefer to speak of a model of definition. Okay, who knows something about algebraic topology will maybe recognize here category of sheaves side, and so we can also consider the third part of the model, SKT model, that means the topos dimension, which here is expressed simply the global meaning of the thesis, or what emerges from as global meaning. And this is the emergence of a topological approach to epistemology of mathematics education by linking different steps and dimensions in a theoretical research within a unified conceptual model. This is all the T part of the model, and yes, okay. This SKT model was also used in order to analyze the single chapters of the three parts of the thesis. Here we can see on the upper left side an example of this analysis applied to the 5 chapters of the first part of the thesis. We can see that the meanings, they are not always global. We have sometimes local meanings, and we ask them to research for a global meaning for a global section, that in order to be able to give a global meaning to each of the chapters. Okay. Let's now come to the evolutionary path of the thesis, some steps. First of all, the answer to the research question 1, which were the criteria we identified. The need for dynamicity. That means that mathematical objects specific to mathematics education should be dynamic. Should be, the definition should be able to describe them as dynamical objects. The existence of mathematical objects is institutionally distinct from the ones in mathematics and the relation between them. This should be explainable in the definition, and then different ontological layers should be able to be put into evidence. That means the first and second order interpretive models. Then also the definition should be absolute generally. That means it should abstract from any reference to some specific epistemological position or learning theory. Then it also should be able to frame technically the relational modality of emergence of such objects. Then it should also be able to take into account the role of semiotic representations in the emergence of such objects. What happens here? The seventh criteria is given by the fact that it should be able to take into account the pragmatist approach to meaning giving to objects in mathematics education. So let's come now to the category theoretical model and the theoretical framework. Okay, I will tell something about some basic concepts of theory category. Category, what the category is, what the functor is, what natural transformations are, and also what a home functor or representable functor is. Okay. What is a category? A category is a very simple structure. We can consider it as composed by objects and morphisms. Morphisms are also named arrows, and we have not to think of morphisms as in mathematical sense. We can also interpret them simply as relations between objects, and also objects have not to be necessarily mathematical objects. So we can use category theory within very different contexts, not only in mathematics, but also in other contexts. So we have here a category composed by 3 objects, the object A, the object X, and the object Y. And we have relations between the morphisms. For instance, the morphism F has A as the domain and X as codomain. And this is the typical that an arrow or morphism has a unique object as domain and the unique object as codomain. This is very important because this means that they are invertible. Morphisms are invertible. And another requirement is that to each of the objects we have an identity morphism associated, here represented by the curved black arrows. And there should also be defined an operation of composition of morphisms, and this operation should be associative. These are all the requirements in order to have a category, and this is really very light are very light requirements. That means that the category is like a monoid, a very general algebraic structure. So what are functors? Functors are the second important concept in category theory. Functors are maps between categories. Here we can see a functor F representing mapping from category A to category B that maps objects in objects and morphisms in morphisms. We can distinguish between covariant functors. They map the morphisms in the same direction as they are in the first, in the domain category. And we can also have contravariant functors that invert the direction of the morphisms. A special kind of contravariant functors are the presheaves that are contravariant factor that map from category of sets to a category C. Category of sets is a category where we have objects that are sets, and the morphisms are functions between sets. Then we can also define mappings between functors. When we take 2 covariant functors and we map between that functor, so we have natural transformations, here represented by the big red arrow. And I would say this is all we should know about. Yes, we should also tell that when we have a contravariant functor, then category, and then it maps into the category, dual category of the starting category. The dual category of a category is simply the category that have the same objects, but have the arrows that inverted the direction. It's also called opposite category. Let's now look to the idea of home functor or representable functor. In order to understand this argument, we have to start with small category. Small category is simply a category which objects are actually sets and not proper classes, but it is not a very demanding requirement. We are also always acting in context where this requirement is satisfied. And we take now the category of presheaves, here represented by set C. We choose an object from the category C, for instance, the category A, and we suppose that this is the object we want to define or to know. Then we let act this functor, home functor called representable functor, and we will see now how this functor acts. It acts in this way, creating a copy of the category C within the category of presheaves, varying on C. The objects the three objects are here sets, and what can we put within that sets? We put within inside of the sets all the morphisms that have the object A as domain, and the object, the set is associated to as codomain. That means that we put inside of the first set only the identity morphism of the object A. Within this second set, we put only the morphism F. And here inside of the third set associated to the object Y, we put the composed morphism F composed G. And we map then also the morphisms. So we have here a copy of the category C, but the particular fact is that this copy of the category C is expressed as a function of a unique object of the object A. And this is the object, as said, we were interested in. What is also very interesting is that the objects in themselves disappear at all. We have no objects here in the copy, we have only relations. And this means that if we imagine to impose a sequence of the relations, we have processes here. So we have a definition of the objects by processes. So this is the object, the home functor, altogether is the home functor. And this home factor is said, named also representable factor, and also sometimes also Yoneda immersion. We said that set C is the set of the category of presheaves, and in that category we have the objects that are functors, and the morphisms are the natural transformations between them. Now, this immersion of done by the representable factor provokes a kind of immersion of presheaves, of other presheaves that are not representable factors. And so we have interactions between the presheaves and that are not representable and the representable factor HA. There are natural transformations. Why this does occur? Because we said that in category theory we have this the invertibility. Duality is a great very important characteristic of category theoretical tools. And so this immersion of these presheaves that are not representable is simply the reaction of the fact that we can invert the direction of the relations between the objects. And so what happens is that the object A in itself disappears, and what remains are only its relations with its context. And this is called by Zalamea the object A in a synthetical sense. By the action of the presheaves, we have then the image of sent back by the context, and that image altogether with their relations between them, the natural transformations between them, represents the object A from synthetical point of view. We can, but what is interesting here is that we can also recover this image here from the blind people and the elephant. If we consider this the action of the representable factor in a metaphorical way, I think you know this representation. It was also used by Susanne Prediger in their plenary lecture at 12, where we have people that do not know what an elephant is, and they are blind, and each of the people touch the elephant and have another idea of what it is. What is interesting for us is that mathematical objects are not elephants, because they do not exist in reality, and we cannot go to touch them. And so we can only experience them. We can experience them in different contexts. And from an object from synthetical point of view is simply the set of all the experiences sent back by this context, rich context of for the object and the relations between them. Okay, what is very nice is that there exists a mathematical tool coming from category theory that describes just the idea of synthetical object, and it defines, it proves that this is that this knowledge, synthetical knowledge, is potentially complete, and this is the Yoneda lemma. Nobuo Yoneda was a Japanese mathematician, and he was the first that theorized this result. It is one of the most important results in category theory. This is the proposition of the Yoneda lemma. The statement, it is very, very nice, very elegant, but it's not important to understand it now. I show it because it exists, but I explain just what it means. When C is a small category and A is object belonging to category C, and F is per-sheaf, then the natural transformations going from the representable functor by the object A and the functor F state in a univocal correspondence with the image of A according to functor F. Okay, but the most important aspects are also explained using the idea of blind people and the elephant. Okay, let's have a look another time of in this distinction about the analytical and synthetical conception of objects, because it's very important. From analytical conception, from this point of view, mathematical object is a set with some property or structure defined on it, as we saw this in the case of definition of function, and the meaning is subjective and is given by the set theoretic denotation of the concept of function. In this case, in Frege's sense, that means it's a subset of the product of the Cartesian product of the sets. There are the domain and the codomain sets. From synthetical point of view, an object, a mathematical object, is completely determined by its relations to other objects. Metaphorically, we can say, tell me who you are, who your friends are, and I will tell you who you are. And the meaning is, in this case, subjective and is given by the uses the subject is able to make of this object in a given context, in the pragmatic sense intended by Peirce, or also Wittgenstein, Lakatos, and Trotta. They are philosophers very often called or used in mathematics education. Here, a short example in reference to the object function. What I said just, we have the definition. The function is a subset of the Cartesian product, and its meaning is subjective and is given by the respective set theoretic denotation. And of the right-hand side, we have one possible synthetical perspective on the object function. This is another characteristic, that the synthetical objects are not univocally defined. We can consider different synthetical perspectives on the same object. Here, for instance, we can see the function as a primitive function of an integral, or as a derivative function, or as an unknown in a differential equation, or as the solution of some specific partial differential equation, or as an entity that can be represented by a graph, by Libor curves, and so on, and also that the function is a relation, and so on. And we can see this rich context that creates the object as such. Let's now come to the answer to research question 2, which are the theoretical fragments that could allow to construct the theoretical framework that could be able to receive the criteria identified in the answer to research question 1. First of all, I want to say something about how we managed to use the metaphorical use of the categorical tools. We used the idea of analogical theory given by D'Amore, and the idea of an analogy given by Pym, or formulated by Pym. It's not important now to study the definitions here. Let's have a look to the representation, to the graphical representations. What we made was to select a suitable theoretical fragment in category theory, here denoted by C, and to create an analogy with a fragment of theory in mathematics education. Then this allowed us to make an immersion of this fragment, of category theory within the category of mathematics education, and creating a copy of the categorical theoretical structure within mathematics education theoretical domain. And so we were authorized to use the structure of the category theoretical fragment, but talking about mathematics education issues. So here an example of how we manage the analogy, the association from different, from the theoretical framework coming from mathematics education, the mathematical categorical model. This I underline the fact that we do not use formalizations. We use only the metaphorical and the conceptual aspects of categorical tools, as we see this also in the SKT model. For instance, in order to model the idea of practice, we use the concepts of category, subcategory, dual category, product category, in order to model the idea of pragmatic meaning or of the semiotical aspects. We used the concept of functor, natural transformation, home functor, representable functor, and so on. In order to model the gnoseological coherence of knowledge in a synthetical sense, we used all the concepts here, evidence in blue, the plain and faithful functor diagram and constant diagram, cone of a functor, limit, complete category, pullback, initial and terminal object, and two propositions. The second one is the Yoneda lemma, we saw former, and also here another proposition, the first proposition that we used mainly in order to justify the metaphorical use of the tools in mathematics education. Okay, let's come now to the end of this part by showing the answer to the research question 3. If it is possible to formulate a definition of mathematical object specific to mathematics education in the theoretical framework identified in answer to research question 2, and that which takes into account the criteria identified in answer to research question 1. Yes, it was possible. And here we have the general model of definition that makes use of the tools I introduced former. Let's consider the category C as the category of mathematics. Here's an arrow. C is the category of mathematics, not the category of mathematics education. I will correct this. Okay, we should not consider C as the category of all mathematics, of entire mathematics knowledge. It is simply a category where we can imagine that our object we want to define is an object of. And this it can be suitable category, for instance, the one represented former in reference to the object function. We make then Yoneda immersion within the category set C. Here, the category set C represents the category of mathematical practice. And so we create the representable functor HA. And this immersion creates the emergence of presheaves and also the natural transformations between them. And this all together are, HA, the natural transformations of the presheaves together are altogether the synthetical A, the object A in a synthetical sense that is known by means of its relations to the context. Here represented in green as AS. But now we have also to recover the dimension of mathematics education where we are interested in. And so we have to create a product category here, the second factor of the product category is the category named here RME. That means the category of research of results of research of mathematics education. We have results, scientific results, or results in observation in the classroom and so on, results in research in mathematics education, and relations between them. So creating this product category, we have objects. They are given by they are other pairs, we can say, where the first element is the object A from synthetical point of view, and the second element is simply a result in mathematics education that can be associated to this object, mathematical object. So when we do a second immersion into the category of the practice of mathematics education research, so we have the object A, is the mathematical object A specific to mathematics education in synthetical sense, here represented by the blue letters and named ADS. Now we need to interpret this general model, because this, I said, this is a very abstract and general model. We can interpret them. Suitable interpretation could be the following one. The interpretations are not unique, so we can also give different interpretations to this model, but one suitable interpretation could be the following one. ADS can be interpreted as the set of the meaning givings expressed by the conceptions, ideas, representations, and so on, and the transformations between them of a subject X, it can be a person or institution, referred to a mathematical object in synthetical sense AS, and to a result REI in mathematics education. If X is the researcher in mathematics education, then ADS is related to the meaning givings and transformations between them of the researcher, or generally of the research community she belongs to. If X is the researcher in mathematics education that assumes the viewpoint of the epistemologist or of the philosopher of mathematics education, then ADS is related to the meaning givings and transformations between them of the epistemologist, or generally of the research community she belongs to. We can see here that most of the characteristics of the criteria we identified in the first part of the thesis are respected. For instance, the pragmatical approach, because we take into account the role of the context of the practices. We can also say that the semiotical aspect is here put it into evidence, because functors and natural transformations between them can be interpreted as semiotic representations and transformations between them. The generality of the definition is also given. In order to, we have here also the first order model put into the evidence by the fact that we have this second immersion within the set of, within the category of practice of mathematics education research. When we want to recover also the second order category, interpretive model that refers to epistemology and philosophy of mathematics education, so we have to do another immersion, but it's not so interesting because it's the same mechanism. In order to recover the characterization of mathematical objects from dynamical point of view, we have to consider another we have to consider two special cases, and also one special case, and we have to consider another special case also to recover the relation from between mathematical objects in mathematics education and mathematical objects in mathematics. Let's see how this can work. Let's consider the first specific case when the category C is simply a category that have a unique object. That means the object A is the unique object of the category C. This is then a trivial category where we have as morphisms only the identity morphism, and the category set C is in this case simply the category set. There are no morphisms despite of the identity morphism that could represent the knowledge of the object from synthetical point of view. And in this case, the representable factor HA coincides with the identity morphism of the object A, and the object A is considered only from an analytical point of view. That means as we are, this it is usual to define mathematical objects in themselves, as the definition we saw at the beginning, the set theoretical definition. Then the special kind 2, the special case 2, in this case, we consider simply that it is possible to imagine an order or pre-order in the category C. That means that we introduce simply temporal evolution in the category C. We can imagine this simply considering that objects are not introduced in the same time, all in the same time, but there is a temporal evolution. Maybe an object is introduced first and then another second and so on. And in this case, we can imagine the mathematical object as varying over time, as sets of presheaves that vary over time. And here we recover also the idea of semiotic bundle, theorized by Alzarello. The semiotic bundle is nothing else than the evolution over time of a set of presheaves where we have not a reference to they are not complete sheaves, but they are presheaves. Okay, it's not so important to go into detail. In this case, we have the mathematical object specific to mathematics education as a dynamical object that evolves over time. And when we consider only an instant TI, then we have a statical object related to that specific instant. Okay. So there are some works we are working on, some topics we are working on, and others they are still in standby.
So, Miglena, are those the examples of what to use that results of your PhD project into, because that is what you started with. You mentioned that your PhD project is purely theoretical, which I find very interesting within the research in math education. So what you are showing us now on this slide is that where that could be useful. Is that, if I understand correct?
Yes, yes. I think it's very theoretical, very abstract, but it's clear that it can be used in some way. It is useful not for go directly in the classroom and examine what happens there, but it is useful from different points of view. For instance, from the point of view of the methodologies, we can adopt new methodologies, we can adopt how that methodologies can be considered from epistemological point of view of mathematics education. It's not possible to speak about certainty in mathematics education, but I think that the use of such methodologies could contribute somehow to render in some cases also clearer the use of the tools we make in mathematics education. I think, yes. Are there other questions?